Thank you both to you and the organizers. It's a delight to join you for me this morning, for you a different time of the day. I'm really grateful for this opportunity. So I'll share my screen. Hopefully this all works.
Please go ahead.
Yes. And can you let me know? You can see my mouse cursor, is that right?
Yeah, right now it's okay. And then if you want some people, what they do, the cursor, or they do right click and get a laser pointer, depends on the machine you have. If it is window, yeah. Exactly, exactly, laser pointer. Okay, great. So Wonderful. We're all set to go. Okay.
Thank you.
Thanks.
So I'd like to tell you a bit about work that we've done in my group on a Python package that is meant to help you if you're interested in superconducting circuits. It does numerical modeling of these circuits for you, and also helps you quantize new kinds of superconducting circuits. Before I jump into that, I realized that the name of the university where I work, Northwestern, is somewhat misleading. And so I just wanted to quickly orient you. We're actually not in the Northwest of the US at all. We're right close by Chicago, so more in the Midwest, in fact. And so this is where my office is, up in Evanston. And I just wanted to share this, and hopefully one day you can come visit, and I would be very happy to show you around. Now, I know that there have been a number of fantastic speakers in this program, some of whom have talked about superconducting qubits, and yet I think that there may be some who are tuning in just today, and some got an introduction but could use a refresher. So I'll say a few words about superconducting qubits at a very basic level, and then go more towards the details of this Python package. So superconducting qubits are circuits made out of superconductors, very simple circuits. The simplest one that in fact is in use is one that you've seen many times. It's just a simple LC oscillator. And you know, as you learned in Physics 101, there are energy contributions from charging up that capacitor. There's magnetic flux through that inductor. And it's simple to see that these two will become the kinetic and potential energy contributions to a Hamiltonian, describing that circuit perhaps first classically, but then upon quantization, you really just get a harmonic oscillator, as you would expect, with a parabolic potential that arises from the inductor, and you see the typical equidistant energy levels. Great. Now, equidistant energy levels is not the simplest thing to deal with if your goal is to actually build a qubit and keep the system constrained to the lowest two quantum mechanical eigenstates. And so a simple thing to do is let's replace this inductor by a nonlinear kind of inductor, a Josephson junction. And what that does to the potential energy is it basically takes this parabola and turns it into something that is a cosine. So close to the bottom of one of these cosine wells, things look a bit like a harmonic oscillator, but as you go up higher in energy, you see that there's a bit of nonlinearity, and the spacing actually initially gets smaller for levels that remain inside this cosine well. And so this is the simplest way to describe what this transmon qubit is, that is quite widely used these days in labs around the world, and also in places like IBM and Google and Rigetti. Okay. Just to give you a flavor of the transmon is not the only qubit. I think there are lots of exciting qubits out there. Here's another one where, in addition, you now add an inductor, and what that does is it takes this cosine and gives it this parabolic background. That's the kind of potential energy that makes up the fluxonium qubit. And then there even more complicated circuits with potential energies that now have more than one variable. And there's some interesting work on trying to build slightly larger circuits like the 0-pi qubit that are hopefully going to be even better protected from the influence of noise in the environment of the qubit. Okay, now what does this Python package do? It's a package that by now is well, in its second year, close to third year, I guess. And it's something that I started together with a former postdoc, Peter Groszkowski, and it's become more popular over the years. I'll give you an impression of that just in a moment. It's all open source, so you have access to it very easily. And I can say a little bit more about how to install it, but I'm not going to dwell much on it. Our motivation to develop this package was several important points. We wanted to share a research tool, first of all, inside our group and not reinvent the wheel each time, and hopefully come to a place where our code, since we shared it, was actually better and optimized in some ways and well documented and such. So we considered it a tool of for our research internally first, and then realized that there were people out there who actually were interested, and so we shared it just as an open source package. You'll see that there's actually some parts to this package that might work quite well for educational purposes, for use in say in an undergraduate class that discusses quantum engineering, and in that context, superconducting qubits. And then this package also has been a nice opportunity here in my group, but then also more broadly for people to join this project and learn about scientific coding. Good. In numbers, this package is now slowly approaching 100,000 downloads on Conda, one of the popular Python package managers that is also available without charge. I think overall a package with 26,000 lines of code is not a large one, but for something that started as a project with a postdoc and myself, we're quite, maybe we're a little bit proud that we've gotten here, and we'll see where the future takes us. Now, what are some of the things that we do all the time in our research and that we thought might be good to solve more broadly in a package that all of us use? So we want to compute energy spectra, right? We need to know what is our qubit splitting between the 0 and the 1 state. Oftentimes we're interested in visualizing wave functions, so we come to a better understanding of the behavior, perhaps in terms of matrix elements, right? So those matrix elements might govern how strongly a superconducting circuit couples to the microwaves that you feed in through a transmission line, for instance. We're certainly interested in estimating coherence times. It's a tricky business, actually, and I could say more about that, but I will move on for now. We're certainly interested in not just describing a single qubit by itself, right? That becomes boring quite rapidly. So the package is meant to provide functionality by which you can simply take multiple qubits and or harmonic oscillator modes and couple them together in a simple way. And once you have such a composite system, oftentimes it is quite useful to be able to perform parameter sweeps, such as over some external magnetic flux, for instance, and observe how the energy levels behave. Many of you, I hope, are very familiar with a package that, in fact, has Franco Nori's name attached to it as well. It's QTIP, the Quantum Toolbox in Python. I believe it's very easily the most popular package in use, not just in quantum information, because it does a fantastic job of doing time evolution, both closed and open systems, and it's grown tremendously over the years. Time evolution, solving the Schrödinger equation or Lindblad-Master equation is only one of the many things that it can do now, and so we don't try to mimic any of that, but what we do is we provide an interface from our package to QTIP so that you can basically feed in your Hamiltonian describing a composite system made up out of superconducting qubits and generate the necessary ingredients for QTIP's MESOLVE or SESOLVE, for instance, and it's a very streamlined way to then go on and do time evolution simulations. And then, sure, there's storing and sharing data and interactive exploration of systems, and I'll show you a little bit of that in a moment. Overall scope, we do lumped element level modeling. So that's the basic assumption that once you have your system, if it's a system that you can represent in terms of a circuit, simple elements coupled to each other, like inductors, capacitors, choices, and junctions, right? Then SE qubits can handle that. And beyond that, we try not to make any additional approximations. We don't expand the cosine of the Josephson junction, for instance. And so things that we do is we look at a selection of hard-coded qubits, like the transmon qubit is part of the package, obviously. Fluxonium, I mentioned, flux qubits, if you're interested in also some of the history of the field, and 0-pi qubit, cosine 2 phi, and other things. So those are all hard-coded, and we try to optimize performance for those particular qubits. Now, once you have decided for a qubit you might be interested in, obviously you want to compute things like the eigenenergies and then visualize spectral properties. We try and make that really easy. Here are a couple of examples of plots. You can look at eigenenergies, see how quickly the charge dispersion in a transmon falls off. You can look at matrix elements, wave functions for fluxonium, wave function here for 0-pi. And so it's we've invested some time in making it relatively simple and streamlined to go from choosing a qubit to actually getting plots very, very quickly that help you understand these systems better. I mentioned coherence times, and I'm probably not going to dwell on them for long, because that's a fun discussion, but it takes some time to do carefully. The upshot is that for the various qubits, we consider different noise channels that are known, and you can produce these overview plots that here show pure dephasing and depolarization contributions to the overall T1 and T phi for a couple of different noise channels that are known to be relevant. Good. And then, yes, I mentioned that one qubit alone is not enough, especially if you're interested in working towards quantum computing. And so building up composite Hilbert spaces is a quick and easy thing with this package. The plan is from here for me to move on and show you a little bit about what you can do. I think one thing that I would like to mention and show you is that there's a very simple graphical user interface that we created, especially for beginners who are not yet great Python programmers. And so if you're interested in that, then what you would have to do is, you must have Python on your computer, and then install this SE qubits package. We have actually pretty good documentation. Let me try and jump to my browser window if I can find it. There we go. So if you Google for SE qubits, and I find my cursor here again, then here's the documentation. I actually don't, Franco, can you do me a favor? Can you see my browser right now, or am I stuck in PowerPoint? You're muted.
Here, I can see your browser, so I see superconducting qubits documentation, and then getting started and overview.
Great, thank you. Yeah, that's exactly what I want to show. Thank you so much for confirming that. So this is the documentation that you get to see online. You just Google for SE qubits and you land on this website hosted by Read the Docs. And we really try to make this simple. So you saw a moment ago the installation steps, which are simple. We've started just last week or so to collect some intro YouTube videos, which are like 4 or 5 minutes long. And you see here one of my undergrad students is actually explaining how to use this graphical user interface that I will show you next if I have to find my cursor here. There we go. So this is really simple. I've obviously installed this package on my machine, and all you do is you import it. That's one line that you can copy and paste if you are not familiar with that syntax. And then the simple thing to do is just you say, we'll call the graphical user interface, that's GUI in short. And this is what you get. I like it a lot. You see in the top row, there's a number of these qubits that you can access. So let's say you're interested in a tunable transmon, and perhaps you're really new to this and you are actually not sure what this is and what all these parameters are. There's a button or a panel here that says qubit info, which shows you the circuit, sort of a schematic of what the device might look like. And then there's the Hamiltonian, and a lot of the parameters that are here as sliders are sort of explained in terms of how they enter into the Hamiltonian. And so what you see is here's the kind of the beginning of the cosine potential. You see a couple of wave functions in there, and of course I now can sort of play with these sliders, and you see that they indeed modify what happens with my wave functions down there, for instance. There's other options here. You can scan the energy spectrum, say over flux. That's what's done here. You can look at matrix elements. Here, for instance, are matrix elements of the charge operator, which are really important for the understanding of what transitions can microwaves actually induce if you couple them capacitively to such a circuit. Well, you know, you can scan matrix elements over parameters as well. That is typically a bit more rich and perhaps complicated. And then there's also ways to look at noise. If I switch here to coherence times, then with a little bit of weighting, which is tough with Zoom, but we'll get an overview plot as the one that I showed you on the slide. Okay, so we think that this graphical user interface is more or less appropriate for people, even if they don't know how to do a lot of Python coding. And it's easy to kind of explore and get some intuition and enter the field in a way that doesn't require you to write your own Python code right from the start. Okay, so I'm going to jump back to my slides if I can manage. So there we go. Okay, so we took a look at the graphical user interface. Those were the 2 lines of code that were necessary. And then we got to see something like that. And then in some talks, I asked the audience whether they actually understand the transmon qubit and what happens with energy levels above the cosine well. And if you're an expert, I wonder whether you're surprised or not that there's actually not a continuum of levels above. Some of my colleagues tend to think so when I ask them first, but that's a different topic. Now, going from here, I mentioned the importance of composite Hilbert spaces. This plot here over on the right shows a transition spectrum for 2 transmon qubits coupled to a single harmonic mode like the one in the resonator. And so you get to scan such a spectrum over an external flux, for instance, and the package makes it quite simple to plot transition spectra like this one, which can be compared to the 2-tone spectroscopy data that experimentalists tend to take to characterize their devices and understand the actual parameters realized in their devices. Good. Now, the last part, I would like to talk a little bit about a relatively new addition to the package, which enables you to define your own custom circuit. So suppose that you're interested in studying something that is not the transmon, fluxonium, or any of the hard-coded qubits in the package. Wouldn't it be nice if you could specify your own circuit and then get the help from someone, in this case just the computer, to generate the corresponding Hamiltonian, find an appropriate basis in which we would represent that Hamiltonian as a matrix, and from there on, of course, do all the numerical calculations needed for obtaining energy levels, eigenstates, and such. And that is something that we worked on for a while, and my graduate student, Sai, is the one who wrote most of the code for that new module. And I'll show you a little bit that gives you a flavor, even perhaps if you've never done circuit quantization by hand. I'll give you a flavor of the fact that a couple of steps are involved in that, and some of them tend to be a little bit tedious. And so it's actually quite nice that we can make some of that automatic. Circuit quantization, here's a schematic of the workflow for that. And you see there's indeed a number of steps. So let me perhaps not go through all of this in detail, but again, give you an overall flavor of what's involved. So you would start with a graph description, perhaps, of your circuit, just saying that they're individual nodes, they're connected by branches, and those branches are elements like capacitors, inductors, and junctions. And then just like you know, Kirchhoff's voltage laws apply to classical circuits, they apply here with sort of a little legal footnote that the external flux that gets threaded through loops in a superconducting circuit is quite important, and has to be incorporated in this Kirchhoff's law, if you will. And there are ways to do that systematically. We've basically taught the computer how to do that for us, and that allows you to first actually get a Lagrangian, a classical description of the superconducting circuit. We go through quite a bit of work in attempting to simplify things and also to distinguish different degrees of freedom. I'll show you the 0 pi potential again in a moment. If you have good memory, you will recall that along one direction, it looked like there was a parabolic background and wave functions should be confined in that direction. In the other direction, it was periodic. I'll show you again in a second if you forgot. And then from there, there are a couple of steps to go from the Lagrangian, now formulated in new and useful variables, to a symbolic Hamiltonian, quantize that, choose an appropriate basis, and then do diagonalization and such. So that is what is implemented. And yeah, here once more, the kind of the reminder, this is what the potential energy looked like for the 0 pi. And you see that indeed in one direction, there's this parabolic background, and you will have wave functions that should be L2 integrable along that direction, but in the perpendicular direction, everything is periodic. So boundary conditions along these two axes actually differ. Okay, now this slide is a bit more technical, and I think we can sort of look at it from a high level and state one more time that different variables, different degrees of freedom, they are associated with different boundary conditions. And so it's important to identify that. So on the quantum side, we impose the correct boundary conditions. And then there are certain types of variables or certain situations where a variable might not appear in the kinetic energy or might not appear in the potential energy, in which case simplifications are possible, which we recognize in the code and carry out. What does that look like in practice? So here's the toy example of a 0 pi qubit. It's a particularly toyish example because that is one of the hard-coded qubits in SE qubits. So no real need to use this custom circuit module, but it's nice to, of course, play with something that is familiar first and ensure that it gives indeed the results that we expect. So once you've drawn a circuit like this, you see that I've already enumerated the nodes of the circuit, 1, 2, 3, and 4. And one way in which we specify this as a graph is just to say, there are these branches, there are 2 Josephson junctions, there are 2 inductors, there are 2 capacitors. You see them over here, 2 junctions to inductors to capacitors, and we specify which nodes they connect, what parameter values are associated with these elements, and then it is actually quite straightforward to just hand over this description. That is what we put into this as a string, and then basically type one more line and get a symbolic Lagrangian first in the node variables that are sort of a good place to start, and then the package does an analysis of boundary conditions, different degrees of freedoms according to their type. It will define new variables, and you'll see, if you're interested in what that variable transformation looks like. And if you're not, you can directly jump to the symbolic Lagrangian in these new variables. It will output them using SymPy. And from there, it's only one further step to writing down the symbolic Hamiltonian and constructing a matrix that can be diagonalized. I see that I'm running close to being out of time. I'll make maybe one more brief comment, which is an important one, and we get that question a lot. The question being, so how large a circuit can you actually handle? And it turns out that it's very difficult and perhaps impossible to give a general answer to that question. I can sort of illustrate that. So suppose that size of circuit, you decide that you want to measure the size of the circuit in terms of nodes. You saw 0pi had 4, that we've managed to do, but fluxonium, if you will, only has 2. And I can guarantee you that there's a particular parameter regime. So I've specified the circuit, it has a certain size, but now if I play with the parameters that characterize that circuit, I can easily enter parameter regimes where it becomes quite hard to do numerical diagonalization. And in fact, so hard that you will have trouble getting it to convergence with, well, with this package, in fact. On the other hand, I know of circuits where hundreds of nodes is just fine. Hundreds of nodes, maybe even thousands. If you have a circuit that only consists of L's and C's, so it's just coupled harmonic oscillators, that is a special case that we recognize as well and treat differently, and it's very easy to handle. It's all, you know, normal modes in the end, and normal mode just described one mode by one mode as harmonic oscillators with the right frequencies. And so it is really difficult to make a general statement and answer that question. What we do appreciate is that as soon as you look at nonlinear circuits, life gets hard quickly because Hilbert space dimension grows quickly. And we have some ways to mitigate that. I'll just sort of flash this last slide here, perhaps. So in composite systems, there's some things that you can do naively, just taking big matrices for every subsystem, which results in one humongous matrix. And that is usually a bad strategy. So as part of the package, we have ways to do a simple-minded form of hierarchical diagonalization where we look at subsystems individually first and diagonalize them individually, truncate in the bare eigenbasis of each subsystem, and then kind of bring all of them together, and that results in much smaller overall Hamiltonians towards the end. It's a strategy that is not foolproof either, but it works well if you have well-defined subsystems that interact only weakly with each other. Good. And I think I will end here and just show you, a lot of the people that have been involved in this project. We're truly fortunate and grateful that we've over the years received funding from several sources. We've been blessed with funding from the Air Force, actually allowing us to pay undergraduates for research, and then the Army Research Office really was the one that got this project off the ground initially. And now there's more work going on because we are part of 2 of these DOE centers, C2QA and SQMS. And I'll just, as the last slide, I'll leave this as a summary and look forward to hearing your questions and hopefully providing answers.
Thank you very much for a great presentation. And then people who have questions there in Kigali, they can type them in the chat section. A question I had is the following, no? Is there a section of the software that can do, let's say, Landau-Zenes Zuckerberg Majorana interferometry or quantum error correction or short custody adiabaticity? So I'm wondering if these 3 different subcases have been considered there or not.
Very, very good question. Some of what you mentioned, I think, would involve time evolution. So if you think about active quantum error corrections with pulses, computing fidelities and such, I would have to engage in doing open system time evolution to establish what those fidelities are. This is something that we do frequently, but it's not just a part of SC qubits. It's something that immediately involves QTIP. And thank you for that. And so that's the interface that I mentioned. It's an interesting point whether we should extend that interface and start having a part of the package that has more helper function to streamline some of this. I think that would be an interesting idea. Right now, the interface is really, you need your operators in Hamiltonian and hand them over to MESOLVE or SESOLVE, and we help with that. But there's nothing that basically is titled Landau-Zenes Zuckerberg. So we don't have something like that in place.
If you have suggestions regarding how to interface better with QTIP or how to improve QTIP, there is a group of programmers, something like 10 or so, who are working on it. I mean, I have people in my group right now also doing it. So feel free to send me a note and I'll forward to the right person. And then to how to enhance QTIP based on the experiences you and your team have, because that's the same for people in the audience. Any feedback on the SC qubits should be sent to Professor Koch, and any feedback on QTIP should be sent to me or the other members of the QTIP team. So by listening to your concerns, I mean, the students, postdocs, and then both packages can benefit from this feedback. So feel free to let us know if you want us to make changes, because we're constantly. Also,
and
since
if I may add one thing, Franco, this is something that I've been guilty of in the past, and it's only through working on our own package that I've become aware of it, and I'm changing my ways. We take these packages, especially QTIP, very much for granted, and I think many people use QTIP, but choose to or don't even consider citing it in their references, and I think it's actually rather important to do that, so that there's money involved in some ways, and grant agencies need to see that we all make use of these packages. So if you're out there and you use QTIP or maybe use SE qubits, consider putting that in your references. There are papers that have been published about these packages, and people have done a lot of work to get us to the place where we can just download a nice package and use it, and it's stable and wonderful to work with.
Yeah, thank you very much. I think it's very important. There have been people in Michigan State, and other places using QTIP. They didn't know they came from our group, so I had to remind them, because as you were saying, it's free, so they take it. The sociology is different. When you look at the DFT people, they always or often cite quantum espresso. So in the DFT, there is a sense that if there is a group of people doing quantum espresso, you need to cite them as a thank you, but also because then they can get more money from the funding agencies to improve quantum espresso. So therefore, it benefits you, because then you can get a better quantum espresso because
Right.
so it becomes like a virtuous cycle where the citations eventually benefit the user because then there is more money. I wish I could have more money to get more people supporting QTIP, but the program managers, they want to see evidence. And I hope that your program and my program get more so I mean, because it's a sociological thing. In DFT is different. In DFT, so regarding the science, you wrote about hierarchical diagonalization. We have a paper some time ago about the fractal superconducting qubit circuits. So we're looking at very complex hierarchical structures, but we didn't diagonalize them. And we had a paper, I can see the reference in FISRE B, that perhaps might be a good match for the hierarchical diagonalization. And it turns out that paper motivated people doing dimensions like this, artificial dimensions, synthetic dimensions. They were motivated by essentially like people at Stanford. And initially they were citing our work. Eventually it became synthetic dimension became a different field in optics. But it was actually motivated by these fractals of the qubit circuit. So therefore, I'll send you the reference because perhaps there might be a good match between the hierarchical diagonalizations and the fractal superconducting qubit circuits, which is something I don't think has been explored so far, and I think could be, given the capabilities IBM and other companies are doing, it could, Google and company, it's something that they might be able to do in the future.
Yeah, if you could share that, that would be great. Thank you.
So I'm looking at the chat, both Omololu, any questions you have there, or because I don't see anything on the two different chats here.
Yeah, any questions, Gali? Okay. So we don't have any questions from here.
But
So
anyhow, let me just make an appeal that for the students, both superconducting qubits and QTIP allows them to do experiments in your laptop, and you can monitor the whole thing. I had talked to experimentalists telling me that they can do experiments even at the airport because they just put the system in their laptop, and then it's a way to save money. Experiments are very, very expensive. So if you make an error, you're wasting a year of time and helium. And if you make an error on a laptop, you waste a few minutes, a few hours, no problem. You can afford to make many errors and then learn from them. So it's like a learning tool. So this is an appeal for learning superconducting qubits and QTIP, both of them, because it's good for students, postdocs, early career, people who want to do essentially experiments on a budget. Essentially, you don't have to have millions and millions of dollars to do it, and sweet parameters. So great. So therefore, I thank you, Jens Koch, for the great overview with very pedagogical, and then eventually all the speakers that will be contacted, some of them already gave us their slides, so they can you can remove anything which is confidential, whatever. And then they will be on the website. There will be eventually when I put all the videos and all the PDF files, the presentations, so it will remain like a document for students, not only in the global South and Africa, South America, but around the world, they can actually access this information. So thank you for the great talk. Thanks.
Thank you, Franco. Thank you, everyone.
Thank you very much. Yeah.